Hello everyone. Good evening to all.
I hope I'm audible now. So, hello everyone, good evening to all. Uh, my name is Sheikh Pandey. I am Prime Minister Research Fellow in the discipline of mathematics at IIT Bhubaneswar. Today we are going to talk about week 4 assignment, multiple calculus. So, before that, I want to announce that there's some problem with my laptop charger and it got damaged and my laptop battery is not sufficient. It is almost around 18% only. So I'll see to how much time I can take the class. Okay, whatever is left, I will complete it in next session, next Friday session. Okay. So today we'll talk about some integration. So let first talk about let us have a look at Riemann integration. Okay, so let P is equals to X and be a partition of AB. Okay, and let xk, sorry, and let tk be a point in this subinterval. Okay, xk minus 1 comma xk is sum of the form. So SPF is basically summation k equals to 1 to n f of tk and del xk. Okay, where del xk is nothing but xk minus xk minus 1. Okay, so this sum is called the Riemann sum. Okay, and we say f is Riemann integrable if the sum converges. In other words, Riemann integrable on AB if there exists a number A with the following property. So for every epsilon greater than 0, there exists a partition, let us say P epsilon of AB such that for every partition finer than P, for every partition P finer than P epsilon, and for every and this and every choice of the points tk in xk minus 1 comma xk, we have this thing as pf, this Riemann sum. Okay, and if this is the case, we say that integral f over integral a comma b is that value a. Okay, fine. So we are going to extend. Okay, before that, I want to mention one thing, one fact. So if f is continuous, then it is Riemann integrable. Okay. So we are going to extend these ideas to several variable cases. Okay. So for that, I will just what I will do. So we will call it as multiple Riemann integral. Multiple Riemann integrals. Okay. So let A is equals to A1 cross A2 cross AN be a compact interval in Rn. Okay, so for our case, let us restrict ourselves to only R2. Okay, 2 only. We comment on Rn, R2. So basically, A1, comma A2 are intervals in compact interval, means both side closed. Compact intervals in R. Okay. Now, what do we mean by the partition of A? Okay. So, if P1 and P2 are the partitions of A1 and A2 respectively. Okay. So that is the case. So the Cartesian product the Cartesian product P is equals to P1 cross P2 is said to be partition of A. Okay. Now let P A. PA denotes, so this denotes the set of all partitions of A. Okay. Now consider a rectangle region. So consider a rectangular region. Okay. So let us denote it by R, which is A comma B cross C comma D, which is nothing but x comma y belongs to R2, such that x is in between A to B, comma y is in between C to D. Okay. So basically, it is. Okay. So let us say this is A. Oh, sorry. So say this is A. This is B. This is your C. This is your D. So this is your rectangle. Now we have to partition it. Okay. Okay, fine. So, so we are partitioned it in small rectangular pieces. Okay. Uh, so a small rectangular piece of width del x and del y with this and height del y has area del a is equals to del x into del y. Okay. Okay. So, so if f is a continuous function, so just wait. So, so this is one kind of partition. Okay. Now, what is the definition? Okay. So, there is give the definition. So let f be defined and bounded on a compact interval. So I in R2. So I is basically A1 comma A2 when A1 and A2 are compact intervals in R. Okay. So if P is a partition of I into M subintervals, I1, I2, IM. So M subintervals means these are uh, these intervals. Okay. So these just wait. So these regions, this region, this region, this region, this region, this region. So all these regions in into M subintervals. Okay. And if Tk belongs to Ik, a sum of the form SPF, so k equals to 1 to m f of Tk into, so now what we have to do is you have to take the measure of Ik. Okay, these intervals. Okay, so this is called the Riemann sum. So we are just extending the Riemann sum in one variable case. Okay. So now we say f is Riemann integrable again if this series converges. So sorry, this sum is converges on I on I if for every epsilon greater than 0 there exists a partition. Okay, am I audible to everyone? Hello, can you please reply? So for every partition P, okay, so there's one announcement. Uh, Today I'm facing some problem with my laptop charger. So my battery is also low. It is around 5%. So I don't think this class will run up to that much time. So whatever I am covering in this one, I will continue in the next class after that. Okay, in the next Friday class. Okay, and I will upload this video on YouTube. This integration part. Okay, so please join in the next class. Is it okay? Okay. Okay, so such that for every partition finer than P epsilon of I, we have, so this is the meaning of Riemann integration in several variables. Okay, so again this A will be called integration of f. Okay, so this will be denoted as whatever your rectangular region is, f is equals to A. Okay, now the thing is, if f is continuous, it is Riemann integrable. So there are different notions to denote the integration. So for double integral, we will denote it like this on a rectangular region. So let us say on a rectangular R f x y, and this is area element dA, where dA is nothing but dx dy, which I have already explained in this one. So if you take the a small rectangle, its area will with length delta x and height delta y, its area will be delta x into delta y. Okay, so this is the area element dA dx dy. Okay, so now we can move towards assignment problems. I will just quickly solve because battery is not allowing me. So the question one is, so always remember, whenever I say this integral dx dy or this integral dy dx, it means that this first integral is with respect to x, this second integral with respect to y. Similarly here, this first integral with respect to y, this is with respect to x. Okay, so this we need to calculate. So this is nothing but 0 to 2 pi. So this first we need to integrate with respect to y. So this will become constant. Okay, so this will be tan x integral 0 to x dy. So that will be x dx. So this will be integral 0 to 2 pi tan x dx. And this is nothing but log of sec x 0 to 2 pi, which is 0 minus 0. Okay, so the answer is 0. Now we'll move to as a second question. So value of the integral. So this is not triple integral. So again, in the same case, this integral will means that limits are from z, limits are of the z. Uh, this means limits are of y, and this is limit of x. Okay. So okay. So this thing will become e. So dz by z dx dy. Okay. So this is nothing but ln of z. So ln of z means log base e, and this is 1 e square 1 to 2 dx dy. So this will, so this is 1. Okay. So 1 2. Now with respect to x, so x square, y we will keep it here. Okay, wait. So it is dz dy dx. Dz, so dy dx, dy dx. So, so this is 1 by x square, 1 by y dy, and this will be 1 to e square. Okay. So this is again ln of y. So ln of y 1 to e square. Okay. So this will give you ln of e square. So this will be 2. So 2 into 1 to 2 dx x square. Now this is minus 2 into 1 by x 1 to 2 limit minus 2 into 1 by 2 minus 1. This will give you 1. I hope up to this it is clear. Okay, so I will stop here, and next we will start in the next session Fubini's theorem and triple integral and other parts, linear approximation and other things. Okay, so I hope to this everything is clear. I can't do anything. Charger is not working, so there's the problem. Is it okay to everyone? Hello? Okay, so then we will meet in the next session. Fine? Okay, fine. So I will close this session. Please join in the next session. Okay, because I will continue this one and then I will start week 5 assignment. Okay? Okay, thank you.